Hello, I'm Sean Billings with Pendulum Surveying. Today we're going to be talking about multi-point localizations with the Javad Triumph-LS. Conformal projections, whether that be state plane or UTM or some custom low distortion projection, are typically the easiest way to work with GNSS-derived geodetic positions in land surveying. The types of projections available are almost unlimited, but may commonly be something like Lambert conformal conic, either one or two standard parallels, transverse Mercator, oblique transverse Mercator, oblique stereographic, and others. However, surveyors may at times require even more customization in their coordinate systems than what these standard projections can offer. It may be necessary to develop a coordinate system with a north reference that is based on monuments rather than some geodetic meridian. Localizations use a Helmert 7-parameter transformation to determine the relationship between two unrelated coordinate systems by comparing coordinate pairs from the two systems by least squares. This video will describe how to perform a localization to determine the relationship of a non-georeference coordinate system to a georeference coordinate system. There are a few things to keep in mind so that we can be successful with localizations. One, as always, you want to set your base in a suitable location free from visible obstructions to satellites, such as being away from buildings, trees, and other structures. We want to use fixed solutions only, whether that be RTK or PPK. We don't want to use any float solutions or standalone solutions for points in our localization. Select control points in suitable locations that are free from visible obstructions to satellites, with good geometry related to the project site. Use precise, undisturbed points, so don't use any leaning wood fence post in this. We want to use something that's precise and is undisturbed. And then we also want to make sure our control coordinates are reliable. So we want to make sure that whatever coordinates that we're following, that they have a high degree of precision and were determined by solid surveying methods. A localization, which is a Helmert 7-parameter transformation, compares coordinates from two coordinate systems. This is understanding a comparison of two coordinate systems is foundational to the next few steps. Known, or design points, may be imported before or after field survey points are collected. By importing the known design points first, the localization may be performed iteratively. Once imported, the operator may tie in matching points that are easily found and accessed. A preliminary localization can then be performed to facilitate finding additional points using stakeout. Once these additional points have been recovered and occupied, they can be added to the localization, either one at a time or all at once for the final localization. For this video, I'll begin by importing the points and demonstrating this iterative approach. However, it is very simple to survey the points first, then later import the known design points and perform the localization after the fact. I'll begin by creating a new project, 2017-09-01B. with my coordinate system set to NAD 83 2011 Texas North Central NAVD 88. I've created an ASCII file of the points I'll be using in the localization, which I will now import into my new project. From the home screen, I select Files, Data Exchange, Import, and then navigate to the ASCII text file. At this point, a preview of the coordinates being imported is shown. Notice the values of the imported points. These coordinates are not state plane coordinates, so I do not want to import them as state plane coordinates. This is the number one source of problems users have with localizations in JField. If the coordinates, which are not state plane, are imported as state plane, the localization will fail. Press Next to advance to the next screen. Pay particular attention to this screen before importing. Notice that the coordinates will be imported to page 1, which is set to a state plane coordinate system. As mentioned, this will ultimately result in failure in our localization because these are not state plane coordinates. I need to import these coordinates into a page with a local coordinate system. To change the page or page settings, click the Page button. Select the page in which the points are to be imported and click Edit to change the settings for the page. Next, select Page Coordinate System to change the coordinate system for the page. The coordinate system for these points does not currently exist, hence the need for a localization. I need to create a new local system for my points. To create a new local system, use the button with the house enclosing a plus. This will create a new local system. The default name of the system is Project Name -1. Because a localization, or Helmert 7-parameter transformation, is a mathematical comparison of two coordinate systems, we must have a coordinate system with which we will compare our local system. By using a system that is already related to planet Earth, such as a state plane coordinate system, our new local system will ultimately also be related to planet Earth. A geographic system can also be used, such as NAD83, which is expressed in latitude and longitude. The software will actually create a projection, and the grid coordinates of this intermediate projection will be used as a comparison to the local coordinates. This projection is transparent to the users and occurs in the background. Regardless of the underlying system used, existing grid system or geographic system, it is imperative that the system used have a geoid model if heights are important in the localization. The default underlying coordinate system is WGS84 ITRF 2008, which does not have a geoid model. For this localization, I will set the underlying coordinate system to the same coordinate system as my project, NAD83 2011 Texas North Central, NAVD88. With the local system now created, Select makes this the coordinate system of the import page. Once imported, I'm taken to the point screen where I can see my points. Now I'm ready to collect points in the field that match my imported coordinates. At the Collect Prepare screen, I see that the page is now set to page 1, the same page that I imported the points. And the coordinate system is set to the new local system, which is the coordinate system for page 1. There's no harm to the localization and storing survey points in this page with this coordinate system. However, it may be desirable to keep survey points and design points of different coordinate systems in separate pages for organizational purposes. For my purposes, I'm going to put my survey points in page 0, which is set to NAD83 2011 Texas North Central NAVD88. I'm now ready to begin collecting survey points for my localization. Note that all of the steps taken so far could be done in the office prior to going into the field. I'll begin by collecting 2 points that are in my imported point list. With these 2 points, I have the minimum amount of information required to determine a transformation from the local system to state plane. This will allow me to create a preliminary localization that can be used to stake out other points in the list that may not be easy to locate. From the home screen, select Localize. Before beginning, make sure that the coordinate system at the top left corner under Design is the coordinate system of your imported points. Check the name very carefully and make sure that it's not similar to the coordinate system name, but it matches exactly with the coordinate system name of your imported points. Select the plus button on the right to add the surveyed points that match the imported points. Now use the plus button on the left to select the imported points that match the selected survey points. I now have 2 pairs of points, L001 and C1 are the same point, and L002 and C2 are the same point. I need a minimum of 2 pairs of points because I am not sure of the rotation between the local system and the state plane system. 2 points will allow the localization to solve a rotation between them, albeit with no redundancy. Match the pairs by highlighting a point on the left and the matching point on the right. then select Link at the bottom of the screen. The elevations are valid in this example, so I will select 3D horizontal and vertical for control type. Repeat the process by selecting the second pair and pressing Link. It's tempting to provide all of the known information to the localization application. In this case, the elevations are just as valid on this second pair as on the first. However, for now, I want to provide the minimum amount of information needed for the localization to be solved. For a vertical translation, I only need one pair of points. So for now, I will only make this second pair of points fixed in northeast horizontal and let the vertical remain free. Notice that the middle columns are now filled with numeric values. The delta N and delta E columns indicate residuals of 0. Is this because I have perfect agreement between the imported coordinates and the survey coordinates? No. The reason there are 0 residuals horizontally is because of scaling. The localization has determined the best fit scale factor between the two pairs of points and applied it. Because exactly 2 pairs of points are required to determine a scale factor, there is no redundancy, thus no residuals. Proceed with extreme caution in such scenarios. It could be that the difference is considerable between the import pairs and the survey pairs. The distance between the two imported points could be 200.000 feet. The distance between the two surveyed points could be 100.000 feet, and the residuals would still be 0. The scale factor would be a ridiculous 2.0, but the residuals would be 0. For this reason, always click Customize to view the parameters of the localization to make sure that the values are sensible. I don't know the exact rotation between the local system and the survey system, but it's good to check. If I had reversed the pairs, then this rotation would have been closer to 180 instead of 0. The rotation thus seems reasonable without any additional checks. The scale is determined by comparing the relative distances of the survey points and the import points. For example, 200 divided by 100 equals 2. In this case, the imported points were on a ground-based coordinate system, while the survey points are based on state plane. There should be some scale difference caused by grid versus ground, but this scale factor is based solely on the divided differences in the relative distances of the two systems. It would be like returning to a survey you did 20 years ago with the total station. You set up the total station on a control point from 20 years ago and backside another control point from 20 years ago. The distance should have been 250.00 feet, but today you measure 250.25 feet. To address this difference, you change the parts per million correction in the total station until your distance matches that of 20 years ago. Of course, no one would do that. Every distance you measured would now be scaled by 250 divided by 250.25, which would be 0.999. A distance measured today will be scaled down considerably. Instead, it is much wiser to use the proper geodetic scale factor between the underlying grid and ground. To do this, check the box next to Scale and select the pie shape button. This automatically calculates the average grid to ground factor of the survey points in the localization. Now there are residuals in the delta north and east columns that were 0 before. The residuals are the same because statistically the 2 points share the differences equally. The delta U, which stands for the generic vertical term up, is 0.00 for the point held in 3D, while the second point has a residual of 0.066 and is in gray. The gray color of the text indicates that this dimension is not contributing to the localization. Recall, I did not hold the vertical for C2L002. I can now see that it is within expected tolerances. Once satisfied with the localization, it is time to save it. The parameters are shown one last time. Upon OK, the localization is stored. The import points are recalculated to their geodetic position based on the localization, and the software returns to the home screen. After a localization, I recommend performing an inverse of a pair of points from the localization. Here I've inversed between L001 and C1, and the distances match the localization residual. Now, with a preliminary localization having been created, I can use stakeout to find the remaining imported design points. I do need to keep in mind that my stakeout accuracy will be limited to some degree by the baseline length of my 2 points. In this case, the distance between L001 and L002 is only 116.4712 feet. For design points relatively near, I will likely be close in my stakeout, but I must accept that distant points will have less accuracy due to uncertainties in the rotation, unless I continue to update my localization with points as I recover and survey them. Now we'll go and find and survey another 2 points, L003 and L004. After collecting L003 and L004, I'm ready to go back to the localization to add these pairs, and hopefully strengthen and improve the localization parameters. In order to check them before adding them to the localization, I select a control type of check for both. The C3 L003 pair looks good at 0.045, 0.032, and 0.025 residuals. However, C4 L4 pair looks to be way out. Observe what happens when I simply select both to be horizontal control without checking. C4 L004 is still not good, but because it contributes to the solution along with the other 3 points, it shares a significant amount of its error with the others and is less easy to identify as an outlier. It's better to start with the minimum amount of information required and add pairs one by one to the localization first as a check and then as a control if they look reasonable. It appears that C3L003 is good and can be added to the localization. However, something is wrong with C4L004. For the purposes of this video, I intentionally collected a bad point on L004 to illustrate how to trap errant points. In a real-world case, perhaps the control point was damaged, or it was the wrong point. There were 2 similar monuments in close proximity to each other. Or it was a bad shot, such as a point under canopy that was not collected with enough redundancy to prove the fix. The person in responsible charge will need to decide if further investigation is required or if the point may simply be ignored. Let's collect one more point and look at a potential pitfall when working with the vertical component of a localization and how to identify the conditions for a perfect storm and how to avoid it. We'll now collect point L005, which is a match to design point C5. Rather than putting pair C5L005 in as a pair, I'm going to hold it as 3D horizontal vertical. Notice the residuals for all but C4L004 are very good. It looks like we have a good solution. Notice that the residuals for the 3D control points are 0.000 in the delta U column. This is because 3 points make a plane perfectly. I provided the minimum information needed for localization to determine a rotated or tilted plane. But notice that even C2L002 is looking pretty good with a delta U of 0.084 without being used as control. But is the C2L002 pair really providing much of a check on the vertical solution of this localization? Let's take a look at the map. Notice that points C1 through C4 are almost in a straight line. Only C5 is nonlinear from the rest. What happens if the elevation of point C5 or L005 is wrong? If the pair is included in the vertical control of the localization, then the reference plane will tilt in order to accommodate. If 2 pairs of points such as C1L001 and C3L003 are included in the vertical control, the plane will tilt on the axis of C1 through C3, down or up depending on the error to pass through point C5. Points on the C1 through C3 axis will be on the only accurate part of the tilted plane, while any points with an appreciable perpendicular offset from the C1-C3 axis will be off considerably. This is why it is important not to rely too much on residuals as your source of confidence in the quality of the results of a localization. As previously mentioned, always look at the parameters under Customize. In this case, the parameters are clearly indicating a problem with the vertical solution of the localization. North inclination and east inclination are rotations around the north axis and east axis. Surveyors are familiar with rotations around the up axis, although we don't commonly refer to it this way. Part of the Helmert 7-parameter transformation results is not only a rotation horizontally, but also a rotation vertically. The rotations can be thought of much like the attitude of an airplane. North inclination is nose up or nose down, pitch. East inclination is wing up or down, roll, while rotation is left or right, yaw. And a Helmert 7-parameter transformation determines all three of these rotations fundamentally. But just because these rotations are determined by localization does not mean these parameters must be adhered to, particularly when better solutions are available. Returning to the parameter screen, the north inclination is 147 seconds, and the east inclination is a whopping 3,972 seconds, which is in excess of 1 degree. Let's look at the localization again with minimal information held for control. Horizontally, point C5L005 looks very good. However, there is something very wrong vertically. Like L004, I intentionally collected point L005 incorrectly to produce a substantial error. In a real case, the person exercising responsible charge would need to determine if more investigation is warranted or if the point can simply be ignored. Now we'll survey in the remaining points and we'll evaluate and create the final localization. Matching the pairs all is checked, I can check the residuals of all pairs. These checks are still based on only holding the two pairs that are only 116 feet apart. Horizontally, both C4L004 and C8L008 are out of tolerance, while vertically C5L005 is out of tolerance. If there are enough control points that check both horizontally and vertically, it may be appropriate to disregard the points that check horizontally but not vertically, and to disregard those points that check vertically but not horizontally from the control links. Of course, it may be that some of the horizontal points were not established with accurate elevations, and that vertical benchmarks were not established with accurate horizontal positions. Knowledge of the control will be crucial in making sound decisions here. For this example, we will consider C4L004, C5L005, and C8L008 to be suspect and will leave them out of the final solution. Including all of the points that were in tolerance has reduced the residuals considerably, as expected. The geometry is improved over the short baseline that I began with, and each point is contributing to the final solution. Even though the residuals look good, it is still important to review the localization parameters. Generally, it is best not to allow inclinations. If inclinations are used, it is important to keep within the bounds of the points held for the vertical control. The tilts could cause substantial error beyond the limits of the vertical control that's being used. This is often referred to as remaining in the box. In most instances, I would forcibly zero the north inclination and east inclination. This raises the vertical residual slightly, but it allows me to work beyond the bounds of the control without concern that the tilt will warp my survey point heights. Finally, it is time to save the results. The localization is complete. This survey was done with a base started from an autonomous position. Now that I've returned from the field, I'd like to relate my work to the CORS network using depots. Notice that before we go to depots, the coordinates for base 1 are very near 5,000, 5,000 in north and east. Depots will shift the geodetic position of the base and all associated points to the base. The local system coordinates are tied to the Earth through the geodetic coordinates of the pair points. If the geodetic coordinates change, then so do the local coordinates. Notice the coordinates for the base are now several feet from 5,000, 5,000. The solution is very simple, however. Simply return to the localization screen. A pop-up notification explains that the localization has been updated. No need to save. Returning to the point screen, the local coordinates are again very near 5,000, 5,000. I can now export points and other files in local coordinates. I can also change the current coordinate system to state plane or any other coordinate system, and view the project coordinates, even those that were imported as local coordinates, in state plane. Ultimately, localization in JField provides an incredible amount of power to the operator to evaluate coordinates comparatively and to determine very precise transformations between two coordinate systems. The process determines 7 transformation parameters. However, the operator should use discretion when deciding which parameters to hold and which to overrule.